In this video, I'll show you how to create the famous simulation called Conway's Game of Life using C++ and raylib. It is by far the most interesting project we have built in this channel so far. It is a project that blows my mind. Here is a quick overview of what Conway's Game of Life is all about. It is a cellular automaton devised by the British mathematician John Conway in 1970. The game is a zero-player game, meaning that its evolution is determined by its initial state, requiring no further input from human players. One interacts with the game of life by creating an initial configuration and observing how it evolves. Conway's Game of Life might seem super simple because it has just a few rules, but here's the cool part. Even with those simple rules, we can see all sorts of amazing patterns pop up. It's like magic how a bunch of squares on a screen can start doing things that look almost like they are alive. You've got patterns that don't move at all, called still lives. Then there are oscillators, which are like the heartbeat of the game, flipping back and forth in a rhythm. And there's even more wild stuff like spaceships, which travel across the screen as if they are exploring space. What's really wild is that with just these basic bits and pieces, you could, in theory, build a computer inside the game. That's right, those blinking squares can do anything a computer can do, just by turning on and off according to the rules. So, even though the rules are easy to understand, the Game of Life shows us something awesome. Simple stuff can come together to do really complex and unexpected things. The Game of Life is a fun way to see how complexity can come out of simplicity, and it gets you thinking about the big picture of how the world works. In this tutorial, we will walk through building a simple but very capable version of Conway's Game of Life in C++ using raylib, a popular graphics library designed for writing video games. In order to be able to follow this tutorial, I expect you to have a basic knowledge of the C++ programming language and a development environment for C++ already installed. I am going to work with Visual Studio Code. Also, we are going to need the raylib library. I have prepared a detailed video on how to install raylib on your Windows computer and use it with Visual Studio Code. You can watch it here. It will help you set up everything on your Windows computer. If you prefer to use Visual Studio, check out the second tutorial I have prepared. It will be linked in the video description. If you use a different operating system, you can still follow this tutorial if you have a working C++ setup with the raylib library. Additionally, if you are new to game development with raylib, I suggest starting with my Pong, Snake, and Tetris game tutorials, also linked in the video description, to make the learning process smoother. Don't worry if you are not an expert in C++. This tutorial will provide valuable insights and help you learn a lot. So if you have set up everything and you can compile and run a simple raylib example program, we are ready to go. Game of Life may seem complex and challenging to develop, but fear not. We will take a divide and conquer approach to make it more manageable. In this tutorial, we will break the development process down into 6 steps, tackling each one individually and building upon what we have accomplished in previous steps. With this approach, you will be well on your way to creating your own version of the Game of Life in no time. So, grab a cup of coffee and let's get started and see how we can conquer this challenging project one step at a time. The first step in building the Game of Life simulation is to create a blank screen and set up the simulation loop. Before we start, it is important to understand the structure of today's simulation. It consists of 2 parts. The first part of the simulation is where we define our variables and our simulation objects, such as the grid. The second part is the simulation loop, which is responsible for updating all the cells of the grid and then displaying the grid. The simulation loop is like the heartbeat of the simulation, running repeatedly until the simulation is closed. In each iteration of the simulation loop, we will update the grid according to the rules of the simulation, and then we will display the grid. All this will happen so fast that it will appear as a continuous movement. Now, let's create a blank screen and the simulation loop. Let's open the C++ starter template for raylib that I have created with VS Code. You can download this template project by visiting this GitHub repository. If you open this template with VS Code, you can see it is organized in folders. We have to open the source folder and double-click on the main.cpp file. If we now compile and run this project by pressing F5 on the keyboard, it displays a bouncing ball example. Cool, our setup works. We are now ready to start developing our project. Let's delete the ball.h and ball.cpp files and all the code from the main.cpp file. Just leave the include raylib line and the main function just like I did. Now let's create a blank screen for our simulation and the simulation loop. First of all, we have to create our simulation window. The simulation window is like a black canvas where we can draw our game objects. We need to specify the width and the height of the simulation window. Let's create two variables to hold the screen width and screen height for our simulation. I am going to use a size of 750 by 750 pixels. Const int window width is equal to 750. Const int window height is equal to 750. To create the simulation window, we have to call the initWindow function. This function initializes a window and takes three arguments: the width and the height of the window and the title. Init window parenthesis window width, comma, window height, comma, quotes, game of life. Now, every time we create a window, at some point we have to destroy it, and we do so with the close window function. So, let's add the close window function here. Perfect. We just created the window, and to draw on it, we use a coordinate system similar to the one taught in high school. Each point on this window has its unique x and y values. The coordinate system used in computer graphics differs from the standard Cartesian coordinate system taught in high school. In computer graphics, the origin of the display is located at the top left corner, with 0, 0 being at the top left. In contrast, the standard Cartesian coordinate system starts from the bottom left corner, with 0, 0 being the origin. In this system, the x-coordinate increases as we move to the right, and the y-coordinate increases as we move up. However, in the top left corner coordinate system used in computer graphics, the x-coordinate increases as we move to the right, and the y-coordinate increases as we move down. This means that a point at 10, 10 will be located 10 units to the right and 10 units down from the origin. We will be using the top left corner coordinate system today. That's why it is important to understand the differences between these two coordinate systems. The basic setup of our simulation is ready. Let's now work on the simulation loop. Let's write a comment first. Simulation loop. The simulation loop consists of three parts. First, event handling. First, we need to check for any events that occur in the simulation, such as quitting the simulation, a key pressed on the keyboard, etc. Second, updating. Next, we update the state of our grid according to the rules of the simulation. Third, drawing objects. Finally, we draw all the simulation objects in their new state on the screen. This step uses the raylib graphics functions to render the objects on the display. Today, we just display the grid. By following these three steps, we can create a dynamic and interactive simulation that responds to user inputs and updates its state accordingly. Now, let's implement these three steps. We start the simulation loop with a while loop like this. While, parentheses, and curly brackets. The while loop is an essential part of our simulation. It runs continuously until we close the simulation. At each iteration of the loop, we perform three key steps: checking for events, updating the state of the grid, and drawing the grid. Let's place some comments to help us organize our code inside the simulation loop. 1. Event handling goes here. 2. Updating state of the grid goes here. 3. Drawing the grid goes here. The while loop will run over and over again until we close the simulation. The first thing we do inside the while loop is to check for any events. Now, inside the parentheses here, we type the condition. Window should close, parentheses, equals false. The window should close raylib function is a very useful function. It checks if the escape key on the keyboard is pressed or if the close icon of the window is pressed, and returns true if that is the case. So, if it returns true, the simulation loop ends and the window is destroyed. Our simulation loop needs two more functions. First, we need to call the begin drawing function in the drawing part of our simulation loop. This function creates a black canvas so we can draw our game objects on. Next, we need to call the end drawing function, which ends the canvas drawing. Lastly, there is something else we need to do. We have to define how fast the simulation should run. We do so by calling the setTargetFPS function before the simulation loop. The setTargetFPS function takes an integer as an argument, which represents the maximum number of frames per second we aim to achieve. Typically, games run at 60 frames per second, but for our game of life simulation, we will set it to 12 frames per second. This slower refresh rate will help us better appreciate the unfolding simulation without it speeding past too quickly. First, let's define a variable at the top of our code to hold our FPS value. Int FPS equals 12. Now we can set the FPS with the following function. Set target FPS parentheses FPS. This means that the while loop and all the code inside it will run 12 times every second at most. This setup doesn't guarantee our simulation will run at exactly 12 frames every second. Rather, it sets 12 FPS as the ceiling. This means our simulation won't run faster than 12 frames per second, but it could run slower depending on the system's capabilities and the complexity of the scene being rendered. Now that the simulation loop is complete, we can run the simulation for the first time. As you can see, nothing is inside the simulation window because we haven't drawn anything yet. But the important thing is that we can see the game window with the title and the dimensions we defined, and that we can reliably close the simulation by clicking on this X icon here. Beautiful. The simulation window is black. Let's make it a dark gray color. Raylib provides several built-in colors, but we will be defining our own colors for this game. In Raylib, colors are represented using a struct called color, which contains 4 unsigned byte components: red, green, blue, and alpha. The values for each component range from 0 to 255, where 0 represents the absence of the color and 255 represents the full intensity of the color. For example, to create a red color, we will create a color struct with the following values. Color red is equal to curly brackets 255, 0, 0, 255. The first three values represent the red, green, and blue components respectively, while the fourth value represents the alpha component, or the transparency of the color. In this case, the alpha value is set to 255, which means the color is completely opaque. So to create a dark gray color at the top of the file, let's create a color struct like this. Color gray is equal to curly brackets 29, 29, 29, 255. Inside the game loop, before the end drawing function, we call the clear background function. Clear background parentheses gray. So when the clear background function is called, the Windows background is cleared with this gray color. This is typically done at the start of each frame of the simulation loop, so that the previous frame's graphics are wiped clean and the new frame can be drawn without any old artifacts or remnants. If we run the simulation now, we can see the simulation window is now gray. Beautiful. We just completed a very basic simulation loop, so we can remove step number 1 from our list. We have made progress. Moving on to step number 2, we are about to create the grid. Before we dive in, let's discuss why a grid is essential for Conway's Game of Life and how we will represent the cells within it. Game of Life unfolds on a two-dimensional board filled with square cells. Each of these cells can be in one of two states, alive or dead. As the game progresses through each generation, the cells evolve based on the states of their neighbors. The grid is the backbone of our simulation. It organizes the cells in a structured manner, allowing us to track the state of each cell efficiently and to apply the rules that govern their evolution. It's what makes visualizing the complex, emergent behaviors of the game of life possible, turning simple rules into mesmerizing patterns. For our purposes, the grid also simplifies the programming challenge ahead. We will represent it as a two-dimensional array where each element corresponds to a cell. To make things even more straightforward, we will use a binary system to represent the state of each cell, 1 for alive cells and 0 for dead cells. This representation allows us to use simple arithmetic to count live neighbors and determine the next state of each cell based on the game's rules. Therefore, in this step, our task is to set up this foundational grid. We will decide on its dimensions based on our window size and the cell size we want. We will then initialize our grid with zeros, representing an initial state where all cells are dead. From there, we will develop functions to draw the grid on our screen, visualizing alive cells distinctly from dead ones, and thereby bringing our simulation to life. We are going to use object-oriented programming to help us organize our code. We will create a grid class. As we are creating a separate class for our grid, we need to separate the declaration of the class and its implementation. This is where the header file and the implementation file come into play. The header file contains the class declaration, including the class name, member variables, and function prototypes. It serves as an interface for the other parts of the program to use the class. On the other hand, the implementation file, usually with a .cpp extension, contains the actual implementation of the class functions. This is where the member functions defined in the header file are implemented. Separating the class declaration from its implementation allows for better organization and abstraction of code, making it easier to manage and maintain large projects. So we will need to create two new files to create the grid class. I press Ctrl+N to create a new file and then Ctrl+S to save it as grid.hpp. I will use the .hpp extension to distinguish the C++ header files from the C header files, which have the extension .h. Now we can start writing the header file of our grid class. Pragma once. This is an instruction that ensures that this header file is only included once in a compilation unit to avoid duplicate definitions. Now we can declare our class. Class, grid, curly brackets, and a semicolon. Public, private, . The class will have a constructor, grid, parenthesis, and semicolon. Now let's think about how we are going to create the grid. We know the width and the height of the simulation window. It is 750 by 750 pixels. Let's make a grid inside this window containing cells of 25 pixels in width and height. To figure out how many cells we can fit across the width and the height of our window, we divide the window's dimensions by the size of each cell. When we divide 750 by 25, the result is 30. This calculation tells us that both horizontally and vertically we can fit 30 cells. Consequently, our grid will be structured into 30 rows and 30 columns, summing up to a total of 900 cells. So let's go back to the main.cpp file and add a new variable at the top, named cell size. Const int cell size equals to 25. Now back to the grid.hpp file. We can press Alt+2 on the keyboard and VS Code will display the second open tab of our project. To construct our grid, we need to know the dimensions of the simulation window and the cell size. So let's give the class this information as an input into the constructor. Inside the parentheses, we add int width, int height, int cell size. With this information, we can now calculate how many rows and columns the grid will contain. So let's create two attributes. They will be private. Int rows, int columns. Let's also create an attribute to hold the cell size. Int cell size. Now we are ready to create the grid. We will represent the two-dimensional grid of the simulation as a vector of vectors. This vector of vectors will be a private attribute of the grid class, and we will call it cells. First, let's import the vector header file. So, at the top of our file, we add include vector. Now, let's add the following line. std::vector, std::vector int cells. Here, we create a vector of vectors that holds int values. We will be representing each cell on the grid as an int. We could use a boolean to save some memory space, but by using an int, we gain the flexibility to represent more than just two states if we want to add more states to our project in the future. Now, let's initialize all the attributes of the grid class in the constructor. We will do so using an initializer list. So, in the constructor here, let's add the following. Colon, rows, parenthesis, height, slash, cell size, comma, columns, parenthesis, width, slash, cell size, comma, cell size, parenthesis, cell size, comma. So far, we have initialized the first three attributes. Now, let's create a vector of vectors filled with zeros for the grid. Cells, parenthesis, rows, comma, std::vector, int, parenthesis, columns, comma, 0, and then curly brackets. This expression initializes the cells member variable, which is a vector of vectors of integers, to have rows number of vectors, each containing columns integers initialized to 0. This effectively creates a 2D grid of integers where each integer represents a cell in the grid. Initially, all the cells are set to 0, which represents a dead state in our simulation. The constructor's body is empty in this case, indicating that all necessary initializations have been performed in the initializer list. The constructor of the grid class is ready. Now we create a draw method that will be responsible for drawing the grid on the simulation window. Void, draw, parenthesis, and a semicolon. Now let's implement this method. We need to create the implementation file first. One quick way to do it is to put the mouse over the unimplemented method. As you can see, VS Code notifies me that this method is not yet implemented. We can click on the Quick Fix button and then select the first option to create the .cpp file and the definition. Perfect. This saved us some time. To draw the grid, we will draw each cell of the grid. If the cell we have to draw is dead, we will draw a gray square. Else, if the cell is alive, we will draw a green square. Let's do it. We have to loop through all the cells of the grid. For parenthesis, int row equals 0, row less than rows, row plus plus, curly brackets. For int column equals 0, column less than columns, column plus plus, curly brackets. Now let's create a color variable to hold the color we want to use to draw the cell. But first, let's include the raylib library. Include raylib.h. Now, inside the draw method, we type color is equal to cells, brackets, row, brackets, column, question mark, color, brackets, 0, 255, 0, 255, colon, color, brackets, 55, 55, 55, 255. This line of code assigns the color green to the variable color if the cell at the specified row and column in cells holds the value 1, and a shade of gray otherwise. That's it. We can now draw every cell. Now, before we draw something, let's talk about how raylib draws simple shapes on the screen. Raylib provides various functions to draw simple shapes on the screen, including rectangles, circles, lines, and polygons. When using any of these functions, we need to specify where on the screen you want the shape to be drawn. For instance, to draw a square, we want to use the drawRectangle function. This function takes 5 arguments: the x-coordinate and the y-coordinate of the top left corner of the square, the width and the height of the square, and a color. In our simulation, the cells are square, so we will use the draw rectangle function to draw the cells of the grid. Let's go back to our code. So, inside the draw method of our grid object, let's draw a square. Draw rectangle, parenthesis, x, y, w, h, color. We need to know 5 things to draw a cell of the grid as a square: the x and y coordinate of its top left corner, its width, its height, and its color. The x is going to be column, but since we are using a grid, we have to multiply this by cell size. Column times cell size. We do the same thing for the y. Row times cell size. Now the width is going to be cell size and the height is also going to be cell size. The last argument we have to provide is the color. And we have a color saved in the color variable. Beautiful. A first version of the grid class is ready. Let's test it at once to see if it works. Let's go to the main file and create a grid object. First of all, let's include the grid class. Include grid.hpp. Now, outside of the game loop, we will create a grid object. We will give the constructor all the information it needs. Grid, curly brackets, window width, window height, cell size. We then need to call the draw method inside the game loop. Grid.draw. Let's run the simulation now. As you can see, our window has become light gray. That's because all the cells in the grid are dead, so we give them a light gray color. But since there are no grid lines, we cannot see the cells. We just see a solid gray color. Let's go back to the grid.cpp file to make a small change. One way to create the grid lines is to make the squares we draw for the cells smaller. Let's make them 1 pixel smaller in width and height. So, in this line of code, here we define the size of the squares to be cell size. Let's make the width and the height of the square cell size -1, here and here. Perfect! Let's run our program once more. Beautiful! As you can see, we now have a grid filled with dead cells, but we can see the grid lines. Let's now create an alive cell to see if our code works for the live cells as well. If we go back to the header file of the grid class, we can see that the cells attribute is private, so we can't access it from outside of this class. So let's create a method that will set the value of a given cell. It will be public. Void setValue, parenthesis, int row, int column, int value. Now let's implement this method. Control plus period and then enter, and VS Code will help us with the typing. It is a good idea to add a check to see if the row and the column values are within the grid. If, parenthesis, row greater than or equal to 0, and row less than rows, and column greater than or equal to 0, and column less than columns, curly brackets. Now it is safe to set a new value to the cell. Cells, brackets row, brackets column equals value. Perfect, our method is ready. Let's go back to the main.cpp file and call it. So, outside of the game loop, let's alter the value of a single cell. Let's say the top left cell. Grid.setValue, parenthesis, 0, 0, 1. And let's run the simulation. Perfect, the top left cell has turned green. It is alive. Let's duplicate this line and let's test it with row 3 and column 2. Grid.setValue, parenthesis, 2, 1, 1. We start counting the rows and columns from 0. That's why we entered 2 and 1 for the row and column in the cells list. If we run the program again, we can see that another cell has become alive. Our grid class works as expected. We have successfully completed step number 2. Now we can start implementing the rules of our simulation. These rules are what breathe life into our simulation, transforming a static grid into a dynamic ecosystem. Game of Life is governed by 4 simple rules applied to each cell in the grid based on the state of its 8 neighboring cells. Here is a quick recap of the rules. Under population, a live cell with fewer than 2 live neighbors dies, as if by underpopulation. Stasis. A live cell with 2 or 3 live neighbors lives on to the next generation. Overpopulation. A live cell with more than 3 live neighbors dies, as if by overpopulation. Reproduction. A dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction. Before working on the rules, let's work on the organization of our game to make our lives easier. So far, we have created a grid class to represent a 2-dimensional array of cells. Let's also create a simulation class that will be responsible for creating a grid object and applying the rules of the simulation on the grid. By encapsulating the game logic within this class, we can maintain a clean and organized code base, making it easier to understand, debug, and potentially extend in the future. First of all, in the main.cpp file, let's delete the grid object we have created. It was for testing purposes only. So we have to delete the include of the grid class here, the creation of the object here, the assignment of values to some cells, and lastly, the call to the draw method. Now we can start creating our simulation class. Ctrl+N to create a new file, and Ctrl+S to save it as simulation.hpp. Pragma once. The simulation class will hold a grid, so let's import the grid class. Include quotes grid.hpp. Class simulation, curly brackets, public colon private colon. Let's create the constructor. Simulation, parenthesis, and a semicolon. Let's also add a private grid attribute, grid. But to construct a grid, we need some information. We need the width and the height of the simulation window and the cell size. So in the constructor of the class, we pass these information arguments. Parenthesis, int width, comma, int height, comma, int cell size. Now we can implement the constructor with the initializer list. We only have a grid attribute so far, so we add the following: colon, grid, parenthesis, width, comma, height, comma, cell size, and curly brackets. Perfect. Now let's create a draw method that will draw the grid on the simulation window. Void draw. Also, let's add a method that will set a value of a cell of the grid. Void set cell value, parenthesis, int row, int column, int value. First, let's implement the draw method. We can press Ctrl+period to implement it. Inside this method, we just have to call the draw method of the grid object, grid.draw parenthesis. Let's also implement the setCellValue method. Void simulation, setCellValue, parenthesis, int row, comma, int column, comma, int value, curly brackets. Grid.setValue, parenthesis, row, comma, column, comma, value. Cool! Our first version of the simulation class is ready. Let's go back to the main.cpp file to test it out. First, let's include the simulation class. Include simulation.hpp. We can now create a simulation object. Simulation, curly brackets, window width, comma, window height, comma, cell size. Lastly, we can call the draw method of the simulation object, simulation.draw. If we run the program now, we can see the grid appears. Cool. We can now start implementing the rules of the simulation. For every cell on the grid, we need to find how many live neighbors that cell has. We will create a method for this in our simulation class. But before this, let's manually turn a cell on the grid alive to work with. Outside of the game loop, let's make cell brackets 3 brackets 4 alive. Simulation.setCellValue, parenthesis, 3, 4, 1. Let's run the simulation. Cool, a cell is alive. We need a method to count how many cells around this cell are also alive. Let's go to the simulation header file to create that method. Int count live neighbors, parenthesis, int row, comma, int column. This function will take two arguments, the row and the column of a cell, and it will return how many of the neighboring cells are alive. The neighboring cells of a given cell in a grid, such as the one at row 4, column 5, are determined based on their relative positions. It is important to remember that our grid uses zero-based indexing, so the first row and column are indexed as 0. Each cell is surrounded by 8 neighbors, one directly above, below, to the left and to the right, as well as one in each of the 4 diagonal directions. Let's examine the positions of these neighboring cells in terms of their row and column numbers, given a cell located at row 4, column 5. Directly above, row 3, column 5. Directly below, row 5, column 5. To the left, row 4, column 4. To the right, row 4, column 6. Diagonal upper left, row 3, column 4. Diagonal upper right, row 3, column 6. Diagonal lower left, row 5, column 4. Diagonal lower right, row 5, column 6. To programmatically represent these positions, we can use a vector of pairs, where each pair contains the row and column offsets relative to the target cell. For instance, the cell directly above is represented by offset values -1, 0, the one directly below by 1, 0, and so forth. This results in a list of offset values for all neighboring cells. In the countLiveNeighbors function, we start by initializing a variable to keep track of the live neighbors. This approach, coupled with understanding our grid's zero-based indexing, allows for accurate and efficient calculation of neighboring cell positions. Let's do it. In the countLiveNeighbors method, we first create a variable to hold the live neighbors. Int liveNeighbors is equal to 0. Now, to systematically assess the positions of neighboring cells relative to any given cell, we are going to utilize the pair data structure in C++. This structure will allow us to represent the row and column offsets as pairs, where the first element of the pair is the row offset and the second element is the column offset. Each offset pair corresponds to one of the 8 possible directions from the target cell, directly above, directly below, to the left, to the right, and the 4 diagonal directions. To store all these offsets together, we create a vector of pairs. First, let's import all the needed libraries. Include vector. Include utility. Now let's create a vector to hold all the offsets. std::vector, std::pair, int, int, neighbor offsets equals curly brackets. And now we populate this vector with the offset values for all 8 neighboring positions. Cool. Now all we have to do is to iterate through this list of offsets and add each offset to the position of the live cell we are checking. For parentheses, const auto &offset neighbor offsets curly brackets. Int neighbor row is equal to row plus offset.first. Int neighbor column equals to column plus offset.second. The last thing we have to do is to get the value of each neighboring cell. But we can't do that yet because we can't access the cells of the grid directly. We must give the grid class a method that will allow us to get the value of a cell of the grid. So let's go back to the grid.hpp file and create a new method. Int getValue parentheses int row, int column. Let's implement it. At first, we need to add a check to be sure that we are given a proper row and column value. We did the same thing in the setValue method. We can copy this block of code and paste it here, but since we use the same block of code twice, it is a good idea to create a method for this block of code. So let's go back to the header file and add a new private method that will return true if the row and column numbers we provided are valid. Bool is within bounds, parentheses, int row, int column. We can now implement it. We can copy this block of code and paste it here. If the row and column we entered is valid, we can return true. else we return false. Return false. Our method is ready. We can now use it in both places. In the setValue method here, we replace this expression with this. Is within bounds, parentheses, row, comma, column. Now let's finish the getValue method. If, parentheses, is within bounds, parentheses, row, comma, column, curly brackets, return cells, brackets, row, brackets, column. Else we just return 0. Now we can go back to the simulation.cpp file and finish the countLiveNeighbors method. We just have to get the value of each neighboring cell and check if it is 1 or 0. If it is 1, we have to increase the value of the liveNeighbors variable. But we can implement the same thing like this. What if we add the values of all the neighboring cells together? Since each cell can be either 1 or 0, the addition of all the values of the neighbors will be equal to the alive neighbors. Let's do it this way. liveNeighbors plus equals grid.getValue, parentheses, neighbor row, comma, neighbor column. Lastly, we have to return the liveNeighbors variable. Return liveNeighbors. Let's test this method in the main.cpp file. We have an alive cell. Let's create some more live cells around this cell to see if the countLiveNeighbors method works as expected. Simulation.setCellValue, parentheses, 3, 5, 1. Simulation.setCellValue, parentheses, 4, 5, 1. Simulation.setCellValue, parentheses, 2, 5, 1. Now let's print to the console the value the countLiveNeighbors method returns for the original alive cell. First, let's include IOStream. Include IOStream. And now we can call the countLiveNeighbors method of the simulation object. std cout simulation.countLiveNeighbors, parentheses, 3, 4. std : end line. If we run the game now, we can see 4 live cells in total, and at the console the number 3 is printed. Cool, our method works. But we have a small problem. What happens if the live cell is at the border of the grid? Let me show you what I mean. Let's remove these live cells and create another one. Simulation.setCellValue, parentheses, 5, 29, 1. Let's also comment out the cout statement or the simulation will crash. If we run the game, we can see that this live cell is at the edge of the grid. How can we count the neighbors of this cell in this case? There are many ways to solve this. The way I prefer is to treat the grid as if it wraps around, creating a toroidal array. This means that the right edge connects to the left edge, and the top edge connects to the bottom edge, creating a continuous surface. In this model, a cell on the right edge of the grid has neighbors on the left edge, and similarly for the top and bottom edges. So in this example, our living cell will have these neighbors. Implementing this approach requires adjusting how we calculate the positions of neighboring cells. Instead of directly adding the offsets to the cell's position, we use modular arithmetic to ensure that the result wraps around the grid dimensions appropriately. Take a closer look at a cell positioned at row 6, column 30 in our grid, which has row index 5 and column index 29. For a moment, consider that we want to identify its right-hand neighboring cell. You might think its neighbor is out of bounds, given our grid ends at column 30. However, due to the wraparound nature of our grid, the right neighbor effectively appears at the beginning of the same row, essentially at row 6, column 1. To mathematically resolve this, we will use this formula. New row is equal to parentheses, row plus offset plus total rows modulo total rows. And new column is equal to column plus offset plus total columns modulo total columns. But what is this modulo operator? The modulo operator returns the remainder of a division between two numbers. So 31 modulo 30 simplifies to 1, because when you divide 31 by 30, the remainder is 1. So if we are at a cell with row index 5 and column index 29 at the edge of the window, its neighboring cell at the right will have the following row and column indices. New row is equal to parentheses 5 plus 0 plus 30 modulo 30, which is equal to 5. And new column is equal to parentheses 29 plus 1 plus 30 modulo 30, which is equal to 0. Cool, huh? Now, what if the live cell is at the left edge of the grid? Let's say it has a row index of 5 and a column index of 0, for example. What are the indices of its left neighbor? Let's put the values in the formula. New row is equal to parentheses 5 plus 0 plus 30 modulo 30, which is equal to 5. And new column is equal to 0 minus 1 plus 30 modulo 30, which is equal to 29. Therefore, by using modulo arithmetic for both row and column indices, we can ensure that any cell positioned beyond the last row or column or before the first row or column wraps around the opposite end of the grid. This maintains the seamless continuous space required for the game of life's logic. Let's do it. Let's go back to the simulation class and edit the countLiveNeighbors method. First of all, our method needs to know how many rows and columns our grid has in order to know if a cell is at the edge of the grid. The simulation class does not know this info. Let's create two methods in the grid class that will return the rows and columns of the grid. Let's go to the grid.hpp file and create these methods. Int get rows, parentheses, curly brackets, return rows, and a semicolon here. Int get columns, parentheses, and curly brackets, return columns, and a semicolon. We are now ready. We can go back to the simulation.cpp file and modify our method like this. Int neighbor row is equal to parentheses row plus offset.first plus grid.getRows %, that's the modulo operator, grid.getRows. Int neighbor column is equal to parentheses column plus offset.second plus grid.getColumns modulo grid.getColumns. That's it. Our method is ready. Let's test it out. Let's go back to the main.cpp file. Let's add three new neighbors to the live cell at the other end of the screen. Simulation.setCellValue parentheses 6,0,1. Simulation.setCellValue parentheses 5,0,1 and simulation.setCellValue parentheses 4,0,1. And let's print its living neighbors. Let's uncomment this line here and modify the cell here, 5,29. Perfect. As you can see in the console, we get the value 3. Our method works fine. Cool, another step is now complete. And believe it or not, we are just a few minutes away from running our simulation for the first time. Well done on reaching this far in the tutorial. The next step is to implement the rules of the simulation. Let's take another look at the rules. There are 4 rules to the game as we saw earlier. But if we look closely at the rules, we can reduce the logic of the rules to just 2 rules. Rule number 1. If a cell is alive, it dies when it has fewer than 2 or more than 3 live neighbors, else it stays alive. Rule number 2. If a cell is dead, it can come alive only if it has exactly 3 live neighbors, else it stays dead. Now let's implement those 2 simple rules. First of all, let's delete the alive cells we have created in the main.cpp file and the cout statement. Now let's go to the simulation.hpp file and create an update method. This method will be responsible for updating the simulation state according to the rules. Void update. Now here is the tricky part. We need to loop through the cells of the grid and apply the rules of the simulation at the current state of the grid. If a cell must be changed from dead to alive, we can't save it to the grid because this will alter the state of the grid and this will affect its neighboring cell state. We want to change all the cells' state at once, but we can't do that. So here is what we are going to do. We are going to create another grid, a temporary grid, where we will save all the changes we make to the original grid after implementing the rules to the original grid. Then we will copy all the values from the temporary grid to the original grid, and we will display the original grid. I understand that this method might not be the fastest one to execute on a computer, but it is the easiest way to achieve what we want. I will prepare a detailed video on ways to make the simulation run faster in the future if you are interested. So let's create another private attribute called temporary grid. Grid, temp grid. Now let's initialize it in the constructor. We add this in the initializer list, comma, temp grid, parenthesis, width, comma, height, comma, cell size. Now we have two grids filled with zeros, and we can start implementing the update method. We can press Ctrl plus period here, and we can start implementing the method at once. Now, in the update method, as we said, we need to check every cell of the grid. That's a nested for loop. For int row equals 0, row less than grid.getRows, row plus plus, curly brackets. For parenthesis, int column equals 0, column less than grid.getColumns, column plus plus, curly brackets. Now for every cell we need to count its neighbors. Int live neighbors is equal to count live neighbors, parenthesis, row, comma, column. Now let's get the value the cell contains. It's either 1 or 0. Int cell value is equal to grid.getValue, parenthesis, row, comma, column. Perfect. Now we can implement the first rule. If, parenthesis, cell value equals 1, curly brackets, if live neighbors greater than 3, or live neighbors less than 2, now the cell must die. But be careful here. We will set the new value to the temporary grid. Temp grid dot set value, parenthesis, row, comma, column, comma, 0. Else, curly brackets, temp grid set value, parenthesis, row, comma, column, comma, 1. That's it. The first rule is ready. Be careful. We need the else statement here. Don't omit it. We need to update the value of every cell of the temporary grid. Now we can implement the second rule. Else, curly brackets, if, parenthesis, live neighbors equals 3, curly brackets, temp grid dot set value, parenthesis, row, comma, column, comma, 1. Else, curly brackets, temp grid dot set value, parenthesis, row, comma, column, comma, 0. Perfect. We now just need to copy all the values from the temp grid to the original grid. Grid is equal to temp grid. Perfect. Believe it or not, the logic of our simulation is ready. It is just 20 lines of code. We are ready to test it out. But our grid is currently empty. Let's create a method that will assign random values to the cells of the grid. Let's create that method in the grid class. We open the grid.hpp file one more time and we add a new method to it. Void fill random. Now let's implement it. Again, we need to loop through all the cells of the grid. For parenthesis, int row equals 0, row less than rows, row plus plus, curly brackets. For int column equals 0, column less than columns, column plus plus, curly brackets. Now we give this cell a value, either 0 or 1. For this, we are going to use the getRandomValue function of raylib. Int random value is equal to getRandomValue, parenthesis, 0, 1. With this line of code, we get a random value, either 1 or 0. Now we can set this value to the cell. Cells, brackets row, brackets column, equals random value. This line of code will fill the grid with random values, with approximately half of the cells being zeros and the other half ones. For better results, we want the grid to have more zeros than ones. We can achieve that like this. In this line of code, let's select a random number from 0 to 4. Int random value is equal to getRandomValue 0,4. Now we will set the value to the cell to 1 only if the random value is 4. In every other case, we will set it to 0. Cells brackets row brackets column equals to parenthesis random value equals 4 question mark 1 colon 0. This way, approximately 20% of the cells will be 1s and the other 80% will be 0s. Now let's go back to the simulation.hpp file and call this method in the constructor. Here, inside the curly brackets, we will fill the grid with random values. Grid.fillRandom. We are ready. Let's go to the main.cpp file and call the update method of the simulation class inside the loop, in the part where we update the simulation. Simulation.update. We can now run our program again. Amazing stuff. Our simulation is alive. The simulation is running at 12 frames per second, and you can see the complex and mesmerizing patterns that arise from the two simple rules we implemented. I really find it fascinating. I have spent many hours just looking at the lifelike patterns that emerge from time to time. It is so cool. The way we structured our code, it is very easy to create bigger or smaller grids. We can change the dimensions of the simulation window and the cell size to make a much bigger simulation, for example. Let's say window width is 1200 and window height is 800 and cell size is 4. That's 75,000 cells. If we run the simulation, we can see it works. Amazing stuff. With this higher resolution, we can appreciate the beauty of the Game of Life algorithm even better. Check out some fantastic patterns that emerge, like this one. I can't stop staring at it. Now, let's close the simulation and change the dimensions again to the ones we had before. With this, another step is now complete. Our simulation is working fine, but we can add some cool features to it to make it even more fun. Let's give the user the option to start or stop the simulation by pressing certain keys on his keyboard. To achieve this, let's go to the simulation.hpp file and add a new attribute to it. Let's call it run. Bool run. And now, in the constructor, let's give it the value false. So here we type run parenthesis false. Now let's create a method that will tell us if the simulation is running or not. Let's create it here. Bool is running parenthesis curly brackets return run and a semicolon. This method just returns the value of the run attribute we just created. We can use this method inside the update method. So let's go to the update method we created earlier. We want to update the state of the simulation only if the simulation is running. If parenthesis is running, again parenthesis, an opening bracket here and a closing bracket here. Now we select all the code of the method and we indent it with a tab. Perfect. Next, let's create two more methods to start and stop the simulation. Back to the header file. Void start parenthesis curly brackets run equals true and a semicolon, and void stop parenthesis curly brackets run equals false and a semicolon. We can now go to the main.cpp file. We want to start the simulation when the user presses the enter key on the keyboard and stop it when the user presses the spacebar key. First of all, we have to know when the user presses a key on his keyboard. Raylib offers a very useful function that does exactly that. It lets us know if a key is pressed on the keyboard. It is the isKeyPressed function which takes a key constant as an argument. Let's see how it works in practice. So, inside the game loop, where we check for events and process them, we add this code. If parenthesis isKeyPressed parenthesis key underscore enter curly brackets. This line of code checks if the user has pressed the enter key. In that case, we have to start the simulation. Simulation.start. Let's also alter the title on the simulation window to know the state of the simulation. Set window title, parenthesis, quotes, game of life is running. Now we need to stop the simulation if the user has pressed the spacebar key on the keyboard. Else if, parenthesis, is key pressed, parenthesis, key underscore space, curly brackets, simulation.stop. Set window title, parenthesis, quotes, game of life has stopped. Perfect. Let's test the simulation. As you can see, now when the simulation starts, it is not running but displays the dead and alive cells. If we press the enter key, the simulation starts running, and if we press the spacebar, the simulation stops. Very cool. But what if we want to speed up the simulation or slow it down? We can manually change the FPS variable and run the simulation again. Another way is to use the keyboard to control the simulation's speed. Pressing the F key will make the simulation go faster, and pressing the S key will slow it down. So we will add a couple more if statements here. Else if, parenthesis, is key pressed, parenthesis, key underscore F, curly brackets, FPS plus equals 2. Now we need to set the target FPS again. Set target FPS, parenthesis, FPS. If the user presses the F key on the keyboard, we increase the maximum FPS limit by 2. Else, if the user presses the S key on the keyboard, else if, parenthesis, is key pressed, parenthesis, key underscore S, curly brackets, if, parenthesis, FPS greater than 5, curly brackets, FPS minus equals 2, and lastly, set target FPS, parenthesis, FPS. We decrease the max FPS value by 2 if the FPS variable is greater than 5. I don't want to decrease it any further because the simulation window becomes less responsive. Let's run the simulation one more time. Perfect. Now we can start and stop the simulation and we can make it go faster or slower. Very cool. Another step is complete. Now the last thing I want to add to this project is the ability for the user to edit the grid manually by clicking on the cell to create his own simulation. When the program starts, the grid must be empty, and the user will have the option either to create his own simulation or a random one. So let's go back to the simulation.hpp file. When the simulation starts, we need an empty grid. So let's remove this line of code where it fills the grid with random values. Now let's go to the grid.hpp file and create a new method that will clear a grid. Void clear parentheses. Let's implement it. It is very easy. We will set all the cells of the grid to 0. For parentheses int row equals 0, row less than rows, row plus plus, curly brackets. For parentheses int column equals 0, column less than columns, column plus plus, curly brackets, cells, brackets row, brackets column equals 0. Now we can go back to the simulation class and create a new method called clearGrid that is going to clear the grid if the simulation is not running. Void clearGrid. In the implementation file now, if, parentheses, not is running, parentheses, and curly brackets, grid.clear. We clear the grid attribute in this method only if the simulation is stopped. Now let's also create a new method that will fill the grid with random values if the simulation is stopped. Back to the header file. Void create random state. Let's implement it. If, parentheses, not is running, parentheses, and curly brackets, grid.fill random. Now let's go back to the main.cpp file. If we run the program now, we can see that the program starts with an empty grid. So let's give our program the option to create a random grid by pressing the R key on the keyboard and to clear the grid by pressing the C key on the keyboard. So in the loop, where we check for key events, we add two more if statements. Else if, parentheses, is key pressed, parentheses, key underscore R, curly brackets, simulation.createRandomState. Now we can add another if statement to clear the grid when the user presses the C key. Else if, parenthesis, is key pressed, parenthesis, key underscore C, curly brackets, simulation.clearGrid. Let's test it out. As you can see, the program starts with a blank grid. When I press the R key on the keyboard, the grid is filled with alive cells at random. If we press Enter, the simulation starts running, and if I press the spacebar, the simulation stops. I can now press the C key on the keyboard and all the cells are cleared. Very cool. The last thing we have to implement is manually editing the grid by clicking on the cells with the mouse. This feature will allow users to customize their starting grid before running the simulation, adding another layer of interactivity to the program. Luckily, that's very easy to implement. Raylib offers the isMouseButtonPressed function, which returns true if a specific button on the mouse is pressed. If, parenthesis, isMouseButtonDown, curly brackets. Now we need to tell this function which key press we want to detect. We want to detect the left one, so we add this constant as an argument. Next, we need to retrieve the current position of the mouse cursor. There is a raylib function for this. Vector2 mouse position is equal to get mouse position. When this line of code is executed, the get mouse position function returns a vector2 struct containing two integers representing the mouse cursor's x and y coordinates on the screen. The x-coordinate indicates the horizontal position of the cursor, while the y-coordinate specifies the vertical position. We can use this information to calculate over which cell the cursor is located. Int row is equal to mouse position.y slash cell size, and int column is equal to mouse position.x slash cell size. Now, all we have to do is to simply change the value of that cell. Let's create a new method in the grid class to do just that. Let's open the grid.hpp file and add a new method to it. We will call it toggleCell. If the value of a cell is 0, it will change it to 1, and if it is 1, it will change it to 0. Void toggleCell parenthesis int row, int column. Let's implement it now. First, we check if we are given a valid row and column values. If, parenthesis, is within bounds, parenthesis, row, column, curly brackets. Now we change the value of the cell. Cells, brackets row, brackets column is equal to not cells, brackets row, brackets column. Our method is ready. We can now go to the simulation class and add a new toggleCell method here. In the header file, we add void toggleCell, parenthesis, int row, int column. We can now implement it. We can limit the usage of this method only when the simulation is not running. If, parenthesis, not is running, curly brackets, grid.toggleCell, parenthesis, row, column. Perfect. Now all we have to do to complete our project is to go to the main.cpp file and call this new method. In the loop here, we just type simulation.toggleCell, parenthesis, row, column. Let's test our code one more time. Now, each time I click on a dead cell, it turns alive. And if I click on an alive cell, it dies. Very cool. With this feature, we can now start playing with some game of life patterns. Check this out. This pattern is called a glider. If I press enter to start the simulation, the glider starts moving on the screen. How cool is that? Since the grid is unlimited in size, because we wrap around the edges, the glider will live forever. Let me show you another cool pattern. If I create a much bigger grid and create this pattern, then let it run for a few seconds, you can see it is a pattern that creates gliders. Amazing stuff. In other words, there are patterns in this simulation that combined can create incredible stuff. Some users have created logic gates inside the game of life with patterns like the ones that I showed you. Some others combined these logic gates and created a CPU inside the game of life. And some very bright individual even created the game of life inside the game of life simulation. This is why I love computers and programming. With just 280 lines of code, we created something so complex and endlessly fascinating. This illustrates the beauty and power of programming, how simple rules and concepts can evolve into complex systems and behaviors. The game of life, despite its straightforward setup, serves as a profound example of emergent behavior, where complexity arises from simplicity. It is a perfect demonstration of how programming can mimic natural processes and even lead to self-replicating structures, much like life itself. Before we wrap up, I'd like to highlight that the project's code has been designed with clarity and ease of understanding in mind, rather than optimizing for performance. This approach ensures that the concepts and logic behind the project are accessible to everyone, especially those new to programming or the game of life simulation. Now you can check out some of my other tutorial videos and be sure to subscribe to my channel in order to be notified when I release a new video. Thanks for watching. I'll see you next time.